second day at PASCO for advanced physics experiments. I'm Dan Burns, joined by my colleague JJ Plank. And what do we got for him here today, JJ?
This is the H/E experiment, right? So,
and Photoelectric Effect
right.
is the product name, right?
Mm-hmm.
And that's one of the main experiments, but there's actually a lot of different experiments. We're going to run through the setup, some of the experiments, do some live data collection, show you some example data, and give you a few tips and tricks about this if you have one or a similar system or considering getting one. So we do need to get it set up a little bit, and we've done a little bit already. The Mercury lamp is on because you want to warm it up for about 10 minutes, and we didn't have enough stuff to talk for 10 minutes while we waited to warm up.
And it gets hot too, so
Yeah.
be careful.
And so there's a track that comes with it as well. So we've already attached the Mercury lamp to the track, and then the Vacuum Photodiode goes on the other end. And if you're reading the instructions, they say to have it about 35 centimeters apart, but most of the setup images show them right on the ends, and that's pretty easy to do, and it works. I wouldn't bother too much about worrying about how far apart they are. But I guess if you didn't have the track, that'd be important to know. And we need to do some connections here. So I have this all unconnected on purpose, except you might notice I have the lower power supply on and a couple of cables coming out. That's because we have that connected to the Franck-Hertz tube for our next production here. And so it's kind of like we're a cooking show, and we've got the cake in the oven for the end. And so that's the Franck-Hertz apparatus. This is photoelectric experiment. So normally this would be off, these cables wouldn't be here. So we need to connect the current amplifier to the vacuum photodiode, and
you'll notice these power supplies, these stacked power supplies here are used, the same power supplies are used for this experiment as well as other ones,
right,
like the Franck-Hertz.
Yeah, both of these, all three of these we'll use for the Franck-Hertz.
Right.
And so this is a BNC connector that comes with it, and I've connected it to the current amplifier. And now we can turn that guy on. And there are a couple of things we need to make sure we have ready. There's a range switch here, and on this one the current is so low that we have it set to 10 to the minus 13 range. So if you're having an issue, that's one of the things to check. Then we want to zero this while we have nothing connected, although that isn't that important because if I push this in, now it sort of disconnects it from the circuitry, and then I can zero it. And you can tell I was playing around with it before we started here, so it's pretty close to zero. But we want to get it right on zero. Should it be positive zero or negative zero, JJ?
Yes.
I'll go with positive zero. It's oh, it just went up to 0.01, but it's pretty close. And then key, I've made this mistake before. Get that back out so it can measure current. So if you go up to a setup and the students aren't measuring any current, check that button. It might be pushed in from the calibration. Then we have some DIN connectors to connect to the interface. So whatever interface you're using, this is a PASCO 850. And we need to connect the current. Yeah. It's a slippery table.
Yeah, the glossy surface on the table, you slide around a little bit, just trying to keep them from sliding.
Okay, who tied this up in a knot?
These power supplies, they stack on top of each other too, and they'll nest like that as well.
But you still got to be careful.
You still got to be careful, yeah.
We're just trying to make some room. I would, if I had a lab table, I'd have each one set by itself.
Right.
So the currents, the way the Capstone file we're going to use is configured, is measuring here in slot A, but you could pick a different one depending on how you plugged it in. And then we also want to measure the, we're going to be doing the reverse voltage to stop the electrons and measure that stopping potential. And so I want to make sure I'm measuring this, which is where we're going to be changing the voltage. And that, I have two different connection points here. I want the negative 4.5 to 0.1 here on the bottom. So that's another thing to check. But we have graphics that really help with this. So I'm trying to do it without the graphics. Might be a good idea to bring them up at the end to check. The last connection is to connect the power supply to the vacuum photodiode.
Yeah, that's the voltage. We're gonna create that stopping potential between the anode and cathode, and we'll talk more about that in a second.
So let's, now that I think I have this ready anyway, let's open up the Capstone file. And so you can download these now on the website on the product page for Photoelectric Effect Experiment. And there's a Capstone file that students could use. It's all ready for them to go with pictures and questions and directions and places for data collection and analysis in the manual. And also there's a Word file that helps them set that up themselves, at least, you know, the important parts. So you don't have to do that, but let's open up that one.
And then the files that are available online for this experiment, they're editable. So if you want to make a tweak, if you want to change something in the Capstone file as well as the Word doc file, it's yours. So feel free to make those changes.
So I brought it up, and you can see it has an image, so most student groups could do these connections for themselves just by going with that image. But there are a few subtle things like this, the selector switch here and there that you want to read the directions for. And it looks to me like we're all set up there. And then there's a page with some predictions. Again, you could change and put in different wording or add some questions.
The workbook file might be locked when you download it. If you just go up to the I think it's the edit menu, there's the ability to unlock the workbook file. Then you can change the stuff on the page.
You say unlock all pages.
Yep.
Yep. And then there's a little bit of theory in here. And so it describes what it is we're looking at. What is a photoelectric effect? What does Planck have to do with it? And they show a quantum well here with an electron.
What does Planck have to do with it?
And so you can see the electron is in a quantum well, and so it needs a certain amount of energy just to get out of the well. If I give it extra energy, then it's got this extra kinetic energy. That's what we're going to be measuring. And that electron looks pretty good, but what if the electron looks pretty sick?
Sick?
It's a quantum unwell. And
it came from an unwell place.
And here we have our some theory continued here, which goes over Einstein's equation and how it relates to the experiment. And you end up with this final equation. We're going to be measuring this voltage. And we have a Mercury lamp and 5 different filters that let through just one wavelength. And we can figure out what the frequency is and do a graph of the stopping potential of the voltage versus the frequency. And we get 5 points. And the slope then would be h over e. And so you can figure out Planck's constant in whatever units we're going to do. We'll demo that. Show you a little more of the hardware in a little bit. And also the y-intercept is the work function, but we'll talk more about that, why it's kind of hard to match that with a accepted value. And then there's more about the setup, how we're going to be changing the voltage, zeroing the current thing. Now you might see here it looks like we're not zeroed, but if you want to check it, you can always just push that in and double check that it's still on 0. And it is. And this note in red is in there just for me. No, it's for anybody. When I practice this, I'm sitting in a chair, and I'm going to be adjusting this knob. But when I do it standing up, I have a tendency to start adjusting the current knob. And so you don't touch it from now on. We leave that guy alone. And let's look a little bit more at the hardware here. So the Mercury Lamp, there's a cover on it.
Which can get hot, so it just...
Yeah, the cover usually doesn't get too hot.
The cover doesn't get hot, but the housing will
gets
get
warm,
hot.
yeah. And so you want to keep this cover on when you're not taking measurements. And what I like to do is just put it in a little bit, then it's a lot easier to get off. But I had it in all the way, so it was a little harder. And then over here is the aperture to let in the light. And so there's a lens cover, and even though it's a vacuum photodiode, it's supposed to respond to light. But if you always expose it to light, I guess it wears out sooner. And so having this cover on is good. There's also in the aperture settings, like right now I have it on. It won't fall.
I thought it was falling.
It's on there. And so I'll just try it out. Can you see that on the? So it's set to 4 millimeters, and then you pull it out a little and you can rotate it. There's a 8 millimeter round aperture, that's the diameter.
The diameter, yeah.
And then there's a 2 millimeter, so you got 3 different choices. The fourth one is, well, you can turn the filter to 0 and then it doesn't let any light through, so that's what I was going to show. Then there's 5 different filters around here. This one says 365 nanometers, then 405, 436. They're all the Mercury lines, or 5 bright ones. 546, then up to 577. So we want to start here at 365. And I did test these with our spectrometer, and they're like right on to the precision of the spectrometer. They're within a nanometer of what we're advertising.
Right.
Not that I don't trust our equipment, but any chance I get to use a spectrometer, I'm gonna take it. But you can put it on 0 too. It's another thing that keeps light from getting in, if you wanted that.
Yes.
Now you might be curious about the vacuum photodiode itself, and so this is an older one that I took apart, and you can see what it looks like. It's a glass housing. You might be able to see the anode, which is a little ring of nickel, and then the cathode is the coating on the other side, and the cathode is a mystery material. We have asked the manufacturer, asked a lot of people what it might be. If you have an idea, it's a vacuum photodiode, what that is, I'd be interested. Mainly, you'd want to know maybe what its work function actually is, but there are, again, some reasons why the measurement wouldn't even match it then.
We've found consistent empirical values for the work function.
Yeah.
But to actually know exactly what that cathode is made of, it's not.
And so if you're interested in that, there's a great book, Advanced Experiments in Physics, Melosinos.
Yep.
And we'll put a link to that in the chat. If you don't have a copy of that, I'd recommend it. I kept borrowing Ann Hank's version, and it really helps understand what's going on with this equipment. So let's go to the first experiment. And again, this file is kind of all set up for the students. You may or may not want to do that. My approach typically was earlier in the year, the files would be set up more for the students, and as the year went, I'd have them do more and more, but they're probably in college doing this, not even probably freshmen, and so they probably can handle setting up this. But it's good to have something they can use if they need it. And we have the wavelength here, and then the frequency. How did the frequency get there? Well, if we go over here to the calculator, you can see right. I guess they just typed it in. They didn't put an equation.
Right.
So you could put an equation in for it. But there are some constants in there for helping and then we've set the current reading.
Yeah, so
it's times 10 to the 14th.
right. What Dan's referring to is the students are going to be reading the nanometer wavelength value off of the filter, right? And they could, if they want, enter that into a table in Capstone, and the Capstone calculator could use a calculation to process that value and
using
output
the speed of light.
Output the frequency. Yeah.
Later, we're going to do an experiment to get the speed of light,
Yes.
so they could go and find that.
Yeah.
So what we need to do is down here, you notice it says preview. We're in sample mode. And so if I click on that, we see, hopefully we see voltage. Yeah, I think we're getting it here. We see the voltage and the current that we're currently reading displayed in the data table. And if I like that, all I do is click on keep sample, and it'll save it in the data table, and then I can move on to the next filter. So let's do this first one. It's 365 nanometers.
So I'm going to pull the shroud off, and so we're going to have light exposing the cathode on that vacuum photodiode.
So, I'm not down here looking into the lights.
Right.
So I think we're okay, but I think in a lab setup, I take some care to make sure that was not pointing in a place where somebody be looking into it frequently. You can get cataracts, I guess. And
yeah, there's UV coming from that mercury
Yeah.
source, and it can be dangerous, so we don't want to look at it.
Yeah. So the current reading is off the scale here. Oh, I did what I said I wasn't going to do.
You turned the wrong one?
Yeah.
You want me to?
Just as an example of what not to do. I can get it back.
Yeah.
Here we go. And so I need to put a stopping potential on to try and stop the electrons with the most kinetic energy, right? There's a spread of them.
Yeah, so that light is incident on the cathode, and electrons are being ejected with some energy. Some of them have more than others, right? The potential well they sit in might be a little bit deeper, but the maximum kinetic energy, we want to try to match that to whatever that stopping.
You want to
potential.
stop them all.
Right.
Got to stop them all.
I have a question.
Question?
Yes. Says is the decimal place of the wavelength from the filter label or from looking up the mercury spectrum?
The filter label does not have that decimal on
No,
there,
it does
so
not.
I would guess somebody looked it up and put it in the data table.
You could also, as Dan said, use a spectrometer, right? So the housing comes off and you can put a fiber optic in there to look at what comes through the filter. So you can measure directly what the wavelength value is.
Or the experiment yesterday we did with the,
Yeah, the student spectrum photometer,
Yeah.
right.
so these all connect.
Yeah.
So that's pretty close. I'm seeing a current really close to 0 there. And so I'm just going to say keep sample. And so that's the stopping voltage for the first wavelength. And once they do one, the others go pretty quickly. I think I'm just going to go to the longest one. We'll get
Right.
2, which I would never do in class, right? I always want as many points as possible, but in the interest of time. So JJ has that on the 577. So I'll move down to there, but normally, again, you wouldn't do that. We'll do some of the others in the other data collection. And you can see now I've got negative current. So I'm not only stopping the electrons, but I'm
Pushing them.
sending them back the other way, right? So I need to lower the stopping potential. So these will be the least energetic with the longest wavelength.
Right, right. That KE max is the smallest.
But they're all long enough to eject some electrons. There's none below the stopping potential. So that's pretty
Right.
close, 0. And so I say keep sample. And again, normally you'd have 5 points. Now I can stop data collection. and go up here to our graph, and I've got 2 points, and if we do a linear fit, I guess the slope is negative 0.408, and if you convert that to EV second units, that's the easiest, right? It'd be 4.08 times 10 to the minus 15th. And notice he has to check me here because he's an expert on Planck's constant. And the actual is 4.136.
Yeah,
that's a pretty low percent error. Now I'm using the 4 millimeter aperture. You might get slightly different precision with the others, and so that's kind of a good thing to do. Have one group do the 2 millimeter, one group do the 4, one do the 8. I found the 8 with this particular tube didn't work as well,
right? And
it could be it's shining on a greater part of the vacuum photodiode on the cathode,
right?
And it's not as uniform. Or
yeah, that's so because the theory would state that we should see about the same curve, and the same values, but I think you're right. I think maybe the aperture is wide enough to where it's exposing more of the cathode, and there might be areas on the fringe of the cathode that aren't quite as uniform in terms of the composition of the material.
But the equipment works well enough so that the concept that the intensity isn't going to change the kinetic energy of the electrons works really well, and that's the next part to this. We have a light intensity experiment where we just get 3 different points. This one has us do it at the 436 aperture, so you want to put that to 2 millimeter and then 436. And notice how he's being safe by putting the cover on.
I'm getting a tan over here.
Yeah. And so this, I'm getting some current here. Makes sense that I have to have a larger stopping potential because we just shortened the wavelength from the 577. So it takes this guy's got a little lag to it, so you wait, and then that's pretty good. So that's negative 1.115. And then now we just keep the same wavelength, but go to the 4 millimeter aperture. And if the theory's right, I shouldn't have to change the stopping potential to keep the current at 0.
436, right?
Yep. Worked a little better yesterday. Going down. And so let's see how much I do have to change. And now it's negative 1.19. Yesterday I didn't even have to move them. I wonder what. But still pretty close. And then the 8. And this one was a little different yesterday. Shouldn't matter. I don't think the earthquake affected this experiment.
Yeah, we experienced a bit of an earthquake, and epicenter was in one of our neighboring towns up near the Sierra, and affected some of our precision alignment in our experiments.
But here we have the results. So if I double the aperture, I'm increasing the intensity. If you go by the area, right, by 4,
right. Yep.
And the stopping potential just went up a tiny bit, and then I've tripled it going up to 8, and it's got virtually the same stopping potential. So the concept, I think, is still something they can pull out of that. This last one takes a little bit of time to measure the data. I think we we'll maybe start on this one, and then we'll show you some results. So what I'm going to do now is not just turn it to the stopping potential, but keep going and go positive, and we're just going to measure the current as we go. So let's turn this guy. So we're going to change the range now. So I'm going from -4.5 to 30. So I go all the way there, and let's see if that's still zeroed, so that's still pretty good on our measurement there. I haven't touched that knob. I only did it once, right? Changing the current knob. So this also is a showing something here. So, oh, we want it on for this one. Want it on 436 and
4 or 8.
You can put on any of those.
Okay.
They do all three. We're obviously
Right.
What do you got on?
It's on
4?
8 right now.
Okay. Guys on. Oh, I know. And we changed the range.
Can't see that side.
Yeah, you would. JJ would have caught that. Minus, that should work. So now I click keep sample. And I just turn this a little bit, give it a chance to settle down a little bit, and keep sample. And I just keep going all the way up to 30 volts. Now, to me, the important part is close to the start here, so I would take a lot more points now, and then I could go faster.
Yeah, because it doesn't change a whole lot.
But you get a visual of the current staying 0. Essentially 0. And then it starts to go up.
Yep.
And once it starts to go up, I start turning it a lot more, like maybe give it a whole volt or so. And so you keep doing that, and then you can do it for each aperture.
Right.
There's an additional experiment in the manual where they would do this for 3 different wavelengths as well, to look at the current versus voltage graph for different apertures, same wavelength, same aperture, different wavelengths.
Right.
But that one isn't in the Capstone file. So let's open up the one with the data. So you'll see there's a file that says Photoelectric Effect with data. And so all the files, all the pages are the same, except it's got answers. And so this one you probably wouldn't want to hand out to the students until after they've turned their lab in. So if I go here, you can see there's a graph with all the points. It also shows up on the analysis page. It's got the slope. They've got -4.06. I think we did a little better with just 2 points, so that's bad. We don't want the students to know that. But I'm sure the standard deviation is better. And it has the questions, and then down here are sample answers. And so, and some analysis. And they do talk about the y-intercept here, which I always got it coming out to about 1.5 volts. And so that theoretically is the stopping voltage, but you have
work function.
Work function.
Right.
But you have things that are interfering with that. We're stopping the most energetic electron. They have a spread of energies. There's a field effect. So as they're coming off the cathode, the ones that come later are interfered with by the negative charge electrons that are still nearby. And contact potential,
Right.
if you read the Melosinos book, actually, if you work it out, the work function should be closer to the anode's
Right.
Work function.
Because of that the concept of contact potential.
But it isn't because of these other factors. And I'm not sure if this happens with our device, but on some of them, the cathode material over time can deposit on the anode.
Right.
But you might think, why not get a piece of zinc? What do you got to do to zinc to do this? You gotta polish it, right? And so this, no polishing needed. And so there's a similar light intensity experiment. That one worked out a little better, but we did that one. There's the full curve for doing 2 of the apertures, and then you could also do the do it for different wavelengths that isn't in this Capstone file. And again, there's answers to the questions. If you remember, we did predictions at the beginning. Now they revisit those. So you could definitely have students do this lab with the Capstone file that have not read about the photoelectric effect yet.
Right.
And they would learn a lot from the experience. And then you might be wondering, well, if I can't check the work function, well, let's see, that's for a different thing. So no, we don't, I put that in the wrong file. So I think we have given you a good overview of all the things this can do. Are there any questions we didn't get to, Janet?
Yep.
No, we answered them all. That's either good or bad. I'll assume it's good. And so we're gonna do a little bit of setup for the famous Franck-Hertz experiment next. Welcome back to PASCO's Advanced Physics Experiment Day 2, sort of a marathon we have going. I'm Dan Burns, joined by my colleague Jonathan Hanna.
Hello.
And we've been having a lot of fun working with the Franck-Hertz experiment apparatus that we have at PASCO. You can see we have a lot of equipment here, but if you just were joining us for the photoelectric effect, the top 3 boxes here we all used with that, and so we just had to add a second power supply, and then of course the Franck-Hertz tube that we're using. So I thought I would walk through the setup of this and kind of talk about the logic behind it. Now, one thing I already did is I connected the Franck-Hertz filament to the tube to this power supply and set it to 3.4 volts because we need to warm up the filament for 15 minutes. And so that made this go a little bit more efficient. Now, how do I know what voltage to set it to? Well, there's a manual that comes with this. There's a Word file. There's a Capstone file we'll be showing you. But it's better to look at the sticker on the top of the tube because some of these have different numbers. And these are suggested values. So if you're writing up lab experiments, double check what values are here if you want to put the values in the lab experiment. But this particular tube said filament voltage 3.4 volts.
Oh, go ahead.
I was going to say we had some other ones that were 2.5.
Yeah, and it's possible too a lot of times with these filament voltages that, I mean, this is, as Dan said, this is a suggested voltage for this particular tube, but you might have to adjust the voltage, slightly by, maybe 0.1 or 0.2 voltage to get the filament voltage just right for the experiment.
The electron flux is, I think, proportional to the square of the voltage. So you get a lot more electrons as you raise it, or fewer, and that can be something you can explore in your experiment. So let's hook up the current amplifier here first to the Franck-Hertz tube. And so this is a BNC cable, and it goes here. And right there, and we want to zero it and make sure it's in the right range. And so Jonathan caught this right before we turned the camera on. I had the range setting wrong, and that can cause problems. Sometimes you want to adjust it, but it's on 10 to the minus 10, and that's recommended and in the instructions. And then if I push this button in, we're disconnected, and we can calibrate this so that it reads 0. And once you calibrate it, you want to leave it alone and release that. So if you're doing this experiment and you notice a student group is not getting any current, that's what I would check first, is that button, because if they have it in, it's not doing anything. Oh, except it's -0.
Yeah.
We want +0. No, if it changes a little, we're good.
Well, you're an optimist, right? So,
Yeah.
Okay.
We have it at 0. So now we want to hook up the rest of this, and we're going to be outputting data. You can just read the numbers off these, so if you aren't using a computer or an interface, you can read it off here, but with this experiment, it goes so much easier to have data captured by the computer. You can do a lot more analysis and explore some other things going on.
You get a lot more data points.
Yeah. Or
Well,
depending on the time you're willing to invest.
Yeah, I know. Yeah. It's
So
much nicer to have the computer do it as opposed to having to do each little data point on a piece of paper.
And so I'm going to hook up this DIN cable for the current amplifier to source A on the 850 interface, because the Capstone file that you can download right from our website now is configured that way, but you can configure it however you want. And then the voltage, well, I've got 4 different voltages. The one that's important is the one down here that I'm going to be just adjusting from 0 to 85 volts. giving the electrons more and more energy as they get accelerated down the tube. That's what we want to read here. The other ones we can just pull off the box. And there are two connections here, so if I look carefully, this is the one, the lower one, I want from 0 to 100. There's also 0 to 200 range. This tube says it can only go up to 85 volts, which is plenty.
Yeah, you definitely don't want to go above that because you do risk damaging the tube.
And so I put that into B again because the Capstone file is configured for that. We'll look at that in a little bit. Now, this is sometimes called a tetrode because there's four different kind of connections. We have the filament hooked up already. Then right past the filament is grid 1. And grid 1, we're going to put a small voltage on it to kind of pull the electrons off the filament and get them into the accelerating field. And so that connects G1 and the cathode. And that is a small voltage that is going to be provided by this power supply.
And since we have a lot of things here to keep track of, I'm just going to mark some of these down so we can make sure we know what we're dealing with. So we got the filament voltage right there, and then G1, the first grid. Let's see, we have that one right here.
There you go.
There we go. Hopefully that stays on.
And then we have the main thing we're doing is trying to apply a voltage to accelerate the electrons so they have the inelastic collisions with the mercury atoms. And that is from the cathode to the second grid, G2, at the end of that potential. And so we can use the same connection to the cathode and then to G2.
Okay. That one right there.
And then finally, between the anode and grid 2, we want to put sort of a barrier for the electrons. So they've got to have a decent amount of energy to make it to the anode. So if they just had an inelastic collision with the mercury atom right in front of grid 2, they're not going to show up in our current. And so that's another thing, a parameter that you could adjust and see its effect. This particular experiment, I think we set it to 10 volts.
Mm-hmm. And again, it does say on the tube itself what the ideal voltages are. Okay. There we go.
So, and again, it does, like he says, it's on the tube. So the cathode voltage that we're just trying to get the electrons off the filament, we're going to set that to 1.5. And we're going to be putting some references in the chat for you. I found one that was very helpful and described experiments they had their students do, adjusting things like the voltage on the cathode and the filament voltage and the stopping voltage, the grid 2 voltage, anode, and seeing how that changed things. And so there's more to this than just repeating the Franck-Hertz one. Then we want this guy to be 10 volts. I really crank them.
Mm-hmm.
This goes up to 12. So 10, 1.5, that's close enough. As long as you record the values you actually used in your lab, those are close enough. I'm not going to. And then we leave this on 0 until we're ready to collect data. So let's open up the Capstone file and take a look at it. Again, you don't have to use this. So there's two. There's one that says Franck-Hertz with data, and then just Franck-Hertz. And so we're going to look at that. But once we show how the data collection goes, we'll go and just open up one that we've already collected data. Actually, that's one you can download yourself and check our analysis. Maybe we made a mistake. Now, let's go through the pages here. So it shows some sample data, a little bit of history on this. So the Franck-Hertz, it was kind of the key piece of evidence that the Bohr model of the atom was worth exploring anyway, showing that energy levels were quantized in an atom. In this case, they did the mercury atom. Was interesting to me is they had no idea about Bohr's paper when they did this. And so some people say they were trying to support the Bohr model. They weren't aware of it. There's an old PSSC film on the Franck-Hertz experiment that in the beginning, the guy doing the lab sort of implies that. He pretty much says they were doing it to support the Bohr model, and then guess who comes on the film at the end? James Franck, and he says, no, we had no idea about it. So I wonder if he was even correcting him on the film, but that was, I recommend that film.
Now also on that page, it has an image of what the, yeah, we are on the same page, yeah, but what the tube looks like. And one thing that you probably want to encourage to do, for your students is you can actually take the tube out. There's 2 screws on the back that you can remove, and you can take a look on the inside what the tube actually looks like. And in the tube here, it's kind of hard to decipher, and I'm not sure how well you can actually see on camera, but you can see that you have your first grid right down there, and then you have your second grid at the top right above it, and just right above that you have the anode, which is very tiny, so I'm not sure how well you can see that. But
and we have a sort of a linear model. Some of them are cylindrical, where the cathode is in the middle and the anode is around it. And at first I thought ours was like that too when I saw that shield there, but no, ours goes.
That's what you see in that PSSC film, I believe.
Yeah. But it's got a schematic there, and then ours has argon gas in it. And the original experiment was mercury. And one thing about mercury, well, it's the original experiment, so it'd be cool to do it, but you have to heat it. And so that apparently is an extra step some people want to avoid. So ours is using argon, which you don't have to heat. I think the advantage of mercury would be you could do the experiment without heating it as a control. And then you see the current go up. There's no dips or anything.
But there's a definite safety advantage with this also versus mercury.
And you could measure the light being produced, like Franck-Hertz. That was the second experiment, which was maybe just as important.
With neon.
No, they measured the mercury.
Oh, with mercury, oh, sorry.
But this one, the wavelength is so short, and it's probably way too dim. To get it bright enough to measure, even if you had equipment, you'd probably damage the tube to get that much current. So we don't measure that. Neon actually produces a visible glow, but that is not the transition that you're measuring from the ground state to the first energy level. It's another one that happens, but it is kind of cool. A friend of mine, David Marasco at Foothill College, has done all 3 gases, and he has a great picture on his website. I think we're putting that in the chat, that shows the neon when there's several inelastic collisions happening for a particular electron. But I think we did pick the one that the main advantage of the argon is you get more crests and troughs, peaks and troughs, so you can get better data. So again, a little bit of reading for the students. There's a picture. It looks just like this, right? Doesn't that picture? I mean, it's uncanny. No, it's idealized, right? There is a photo of it, but when I was looking at this, I noticed in the photo they left the ground off the filament. So we did better than the photo.
Whoops.
They're not supposed to use the diagram. And so we've already done all this, at least hopefully we have. And so we are ready to record. Looks like everything's rocking here. We got this on. It's connected. And so you say record. Well, now what I'm going to do is turn this voltage dial from 0 to 85 volts and take the manual suggests 3 minutes. And so that's kind of slow. So I'm not going to do the whole thing. And you could challenge your students because there's various techniques that you might try using to get the smoothest data. Because again, there is a little lag in the power supplies when you collect. So let's see this. So I'm going to start turning it. And at first it's just a whole lot of nothing because we have that contact potential to get over, and then also the first energy level from the ground state. Then it starts to go up. So what I'm doing is just kind of taking my 2 fingers and sort of walking along the dial. That was the technique I settled on. I tried to get one of our engineers, John Hanks, to make a little stepper motor powered gripper that would do this for me, and he had better things to do. And so you can see we got that first peak, second peak, and a third. And keep going up to 85. I think I'm just going to go and get data that's already done there for the sake of efficiency, but nice and smooth. If we expand that before I go look at the complete data, let's stop. And so real easy to measure good values off that. This first peak is real sensitive to the values that you put here, and so you can play around with it, make some adjustments to maybe make that a little tighter. Let's go and look at the final data here. Well, before we do that, let's just show the analysis we would do with this. So what I need to do is measure the voltage at each peak and each trough and put that in a data table. And so Capstone makes that real easy. It's kind of 2 choices. Jonathan said he wanted to use the coordinate tool, and he can just put that guy there and drag it around and say, oh, there it is, it's 33.4. There's also another tool that I ended up using. It's pretty much the same thing in this case, the multi-coordinate tool. And so I just watched the current values. I went across, and when I see it's at its greatest, 9.161, then I would look down there and pull off the voltage.
And one advantage to the coordinates tool also is that it has a delta tool built into it, so you can find the difference between the peaks.
Right. Or you can...
Or you can use the calculator too.
Well, yeah.
Do the old-fashioned way.
That's in a lot of experiments, so that is very useful.
Yeah.
So you would go and do that. So let's look at the one with data. So this has the same pages we saw with instructions and things, but there's, answers in the analysis and some sample data. And so there is completing it, and they went a little past 85 volts, but they might have had a tube that, I think some of the tubes go up to 100 volts. So you want to look at the tube. There's another word of caution in the manual that it says really keep a close eye on the current when you're measuring this. If it just starts shooting up vertically, you should turn the voltage all the way down and turn the filament voltage down some. I think as time goes on, the characteristics of the tube might change a little. Yeah. And so that's in the directions it tells the students that'd be something to talk about with them. And so they had all those peaks, all those troughs, and if you go to the analysis, the graph is on that page too. And so it makes it real easy. So we went across and measured all the peak voltages, all the trough voltages. I think we put a calculation in to calculate the difference. And so the delta tool does it, and here they have a little calculation that just subtracts the two in the calculator page. And then you can have it take the differences and calculate the standard deviation and the trough differences and the standard deviation. You can see we got kind of different numbers for the difference between the peaks and the troughs. And there are reasons for that. When you're at a peak, there's a lot more electrons, and there's a spread of energies there. And so they're spread out. Measuring the exact peak is a little trickier. And there's really 4 different possible transitions from the ground state to that first energy level. It's really spread over really 4. And all 4 of those are possible there around the peaks. But everything I was reading, we have some references if you're interested in this. At the trough, when there's a lot less electrons involved, 2 of those energy transitions dominate, and one of them really is the main one. That's 104. I have it written down somewhere. Well, it's the 1s2 transition, and has the 104.8 nanometer, 11.83 electron volt energy. And so if you want your students to compare what they measure with the actual energy transition, it's not an easy thing to do. There's 4 there, but if you read the literature that we link to there, you can at least give them some guidance on that if you want. Now, I mentioned my friend David Marasco. He had a different twist to the analysis that I thought was pretty slick. And so he doesn't have his students calculate the differences in the voltages and get an average. He makes a graph. So we can just do it right here. And we're going to graph, well, first let's do the peak voltage versus, well, just the number, which on here is a choice is index. And let's get rid of those connecting lines and do a linear fit. And so the slope there tells me it's 11.2 volts per delta in the peaks. And so it's a little different from the 11.08, and it's also plus or minus 0.25 instead of 1.15. So it's a better analysis technique. And then we can also put on the same graph, I can say add a similar measurement and do the trough. And that gives me 11.7 plus or minus 0.042. So notice how much similar, it's much similar because there's not as much spread in the data. So the trough voltage is easier to compare to a theoretical value, and we usually get better data. When I first did this, I go, wait a minute, shouldn't the trough line be below the peak line? But it's that first trough comes at a higher voltage, so it threw me at first. Didn't throw Jonathan. It's just like, come on. And then you can have them do the analysis to figure out the wavelength associated with the energy. There's a voltage, you can put it in electron volts, and this goes through an example. And down here it says the accepted value for the wavelength is that most probable one, the 104.8. And in this experiment, we measured 106 plus or minus 2 nanometers with this data. I went through this half a dozen times, well, completely a half dozen times, much more than that. I was enjoying it. I got much better data than that most of the time, usually within a half a nanometer of that. So I do think that is a good value to have them compare it to. And let's see here. We talked about why argon. I think we covered everything. And so there are, again, a lot of great reading in the chat if you're interested. Some of it is them measuring what these energy transitions are, and that's where I got some of the information. And then that great paper showing how students varied these different parameters to sort of see what's optimal. But it actually agreed with most of the values we had, so that was good to see.
Yeah.
And when we come back, I guess it's speed of light.
All right.
And we'll hopefully see you in just a few minutes.
All right, welcome back for some more advanced physics experiments from PASCO. This session is going to be an explanation and a demonstration of the speed of light apparatus. It's one of our classic experiments and one of my favorites. We are going to experimentally determine the speed of light. And let me explain to you the components that come with the kit when you buy it. So in the kit, you've got this optics bench here, which is what we're going to use to make all our alignments of all the optics. It has a graduated scale on the side of it there. There's a metric scale glued to the side of it there. And I will start from that end. So that is the mini laser. And we use this laser because it has a little L bracket that we use to magnetically connect to this laser bench. And so there's a laser bench aside from the optics bench. And that bracket lets us adjust the height of the laser. So we've had lasers in the past that you can just kind of stick on there, but you can't adjust the height of them. You can adjust the tilt angle, but moving it up and down can be difficult.
So it's a Heaney. Could you use this?
Yeah, so in theory, right?
This is just easier.
Yeah, the experiment is real mechanical. It's real straightforward. And so any laser, in theory, could be used, right?
How did Foucault do it then?
Not with a laser.
He'd even be more famous.
Yeah. So the laser, the height of the laser is important because we want to sort of align the beam in this plane, this optical path here that goes through the setup. And so adjusting that is important. In fact, aligning this thing is probably the most complicated part of this whole experiment. The actual theory behind it and the data collection is not really that complicated. And so the next piece here is a component holder, and we've got a lens on there, right? And so it's a convex lens. That one has a 48 millimeter focal length, and then there's another component holder right here, except this one has a lens with a 252 millimeter focal length. But in between those two lenses is this microscope housing, and there's two parts of the microscope housing. There is the microscope part with a micrometer that'll adjust it. It'll move it back and forth like this. But there's also a beam splitter down there. And so the beam splitter, you can't see it. It's difficult for you to see, but in this housing, directly behind this knob here, there is a partially silvered mirror.
Yeah, students can easily see it here. We just don't want to move it, right?
Yeah, and so just even me touching it, yeah. I pre-aligned this, and just me touching it may have put it out of alignment a little bit, but we're going to go through the alignment because that's oftentimes, like I said, the most difficult part.
And you can, if you have your own optics, you can use those, right? You can buy this separately from the optics, or you get the complete kit.
That's right, yeah. And one of the most important parts of this setup, well, actually, I'll get to that in a second. So the beam splitter, so we're going to send the beam down this bench through both of these lenses, and it's going to get split in half. Or excuse me, I shouldn't say that. It's going to go through this beam splitter here, and it's going to continue down through the second lens there, and it's going to hit this component, which is probably the most important part of this system. It's the high-speed rotating mirror, right? And so there's a mirror in here in this housing, and this housing actually comes with a shroud that sits on top of it like this, and you can thumb screw it down. And the reason it comes with a housing is it spins so fast, it is really loud. It can get really loud. Well, it's not that loud, but it can be loud, and so this helps knock some of that noise down if you're in a classroom with several groups working on the same project. But there's a motor here. Ooh, did you see that? Just me pushing on it, move the alignment. So there's a motor here, and that motor is connected to a motor controller, which is right here. Right, and that motor controller controls how fast that mirror rotates, basically.
2 speeds, right?
Yeah, and so it's got
plus or minus.
Yeah, it's got 2 speeds. So the previous version of this setup had a like a potentiometer control, right, where you can adjust it through a set of different angular frequencies, or excuse me, angular speeds. This one is configured to, you push the button and it ramps up to one maximum, right, angular speed, and then ramps down and changes direction to some other maximum angular speed, which is what we need to do for the experiment. So it's sort of convenient for us.
Then it go to 750 and then double that.
That's exactly right.
Because when it's going really fast, it can heat up the motor, and that's when you want to collect data.
That's right, yeah.
Fast.
Yeah, so we want to spin this thing as fast as we can. And I'll explain the details of that in just a second. But from this rotating mirror, that beam comes down this bench, hits that rotating mirror, and goes down far field down there. And I don't know, you guys can't see it, but there's a fixed mirror, they call it, way down there, right? So this would be like down the hallway or on the other side of the classroom, right? And you can put it at different distances. And so this fixed mirror is going to catch the beam down there and then send it back, right? So
it's like a focal length of something like 15 feet or something.
15 meters, yeah.
50 meters.
Yeah, so it's something like that. It's like, it was either 13 and a half or 15.
So you want to be roughly, that would be the optimal distance to have it, but that's not something you can always do.
Yeah, and that's because as the beam comes through the optics, it's starting to diverge. This lens will do some collimating, right? But naturally it's sort of diverging as it goes down there, and so having the curvature to that fixed mirror, right, it's not perfectly flat, does a good job of sending the beam back here at about the same diameter, right, as it left. And so, and the reason we need that is because the beam goes down, hits that rotating mirror, goes down to the fixed mirror, comes back, hits this mirror again, and then comes back down our optics, and that's now the beam splitter plays a role, right? Now some of the beam gets reflected up through this microscope housing, and we can basically measure the position of the beam, right?
It's going to shift.
Yeah, and so, like I said, the actual experiment, the theory behind it's real simple, right? You've got light that comes down, it hits this mirror, and it goes down to that fixed mirror, and if this mirror is rotating fast enough, right, by the time that light reflects off that fixed mirror and comes back, this will have turned a little bit. And so the optical path here has changed. And so the faster it's spinning, the more the path has changed, the more it's sort of diverged, and that's what we're going to use that microscope housing for.
That's the thing that's really, or the PASCO engineering has really done, is you get such a fast rotation, you get a large shift, you get an accurate measurement.
Yeah, and we said 1500, right? It's not
per second.
That's not revolutions per minute. That's revolutions per second. And so there's a lot of precise engineering that's gone into this housing. In fact, the mirror itself is a piece of metal, right? A flattened piece of metal that has been polished, highly polished to be reflective, because that way there's no like pieces in there that can come loose. Because at 1500 revolutions per second, things are really moving.
That's like a millisecond pulsar.
Yeah. Okay, and so that's basically it for the components. I talked about the motor control. Oh, the last couple of things I want to talk about, there are a set of polarizers that come with it. So part of the alignment is looking into this housing to see if we can see the spot, right? And if we shoot a laser straight down this system and it's reflecting straight back up in there right into our eye, we're going to be in trouble.
Bad, yeah.
So we don't want students to do that or us to do that. So we'll use some polarizers here to sort of quench the beam before it goes down there. Make it nice and dim so we can see it. And then the final components are a couple of alignment jigs. And so these are intended to be put right on the bench, right? And you butt them up against, there's a little bit of a wall here on our optics bench. And so you can put them in two places and the beam should go right through them. Oops, got backwards. And that sort of demonstrates the alignment, right? It helps you align the beam down the length of the bench.
But we already did that.
Yeah, but also my secret is I rarely use these because I find that although they're a good sort of starting place, once you've got the optics in place, it's better to sort of just adjust things by hand.
You move the lenses.
Yeah, exactly right. And so those alignment jigs, I'll sort of set them aside over here. And so alignment. So the way that I align this, right, initially is we want the beam coming straight down, hitting this fixed mirror, or excuse me, rotating mirror, and then send it down to that fixed mirror. So what I do is I make sure the beam comes down through all the optics, right down the centers, right? And so you can adjust that up or down or tilt it. So there's a foot under here that you can adjust. So it's going right through the center of that lens, about the center of that beam splitter. That's a little difficult because it's kind of tilted. You know, it's a 45-degree angle right now. But make sure it's set to a 45-degree angle when you're doing your alignment, because if you don't, right, it changes the path of the beam as it goes through there, the glass in that beam splitter. And so if you align it with it not at 45 and then you turn it to 45 for your experiment, it's going to move.
But that dial, as long as you have it all the way down, it's 45.
That's
so
exactly right.
Pretty foolproof on that.
And so straight through this lens, and then we want to strike this mirror, this rotating mirror, right in the middle, right in the center. And so what I do is I turn it around backward. So this rotating mirror assembly has a little hole here behind that rotating mirror that I can put my finger in, and there's a flywheel, right? And that flywheel, I can adjust it with my finger. The one thing that I want to make sure I do first is there's a plastic thumb screw back here. It's used to lock the flywheel for, you know, transit, packaging, that sort of stuff. Make sure that that is unscrewed. If you have that tightened down and you turn that motor on,
Then you're screwed.
It's a bad, it's a bad situation. So make sure that this thumb screw is loosened, right? And now I can freely, with my finger, move this rotating mirror. I can rotate it, and you can see the beam sort of going around here, right? And now what I want to do is I want to send it down the downfield, right, to that fixed mirror. And so I just rotate it until and you guys can't see this, but I'm sending it down there sort of near the mirror, right? And now what I'm going to do is I'm going to go down there and I'm going to put the mirror where the beam is, and then make sure it comes right back to where it left from. And so this is sort of a two-person thing. Dan's going to help me. I'm going to go down and adjust it, and he's going to watch to see where the return beam is coming to. And there's actually a horizontal and vertical line on the front of this to help you align it. But we basically want it to come right back to where it was leaving. So I'm going to go down. Oh, and I should say that fixed mirror down there is sitting on a tripod. It's a camera tripod. It's not required that you use a camera tripod, but boy, it makes alignment way easier, because rather than trying to get the beam to hit the mirror, I can send the beam down there and then move the mirror to the beam. And so I'm going to go do that.
Now, I wanted to do this, but we're having a step contest here at PASCO, and JJ's a little low for the week, so he wanted to get a few more steps in, so I decided I would let him do this part. Oh, I see it.
You see it?
It's a little low and to the left.
Okay, so
And that's you went a little. That's pretty good height-wise. Still a little to the left. And now you're centered. Bring it down a little. Just a little bit, tiny bit. And it might have moved a little right as you did that.
okay, so let's.
You probably want to look at it.
Yeah.
Then you can get more steps in.
Yes, I'm getting my steps in. So I can, you know, it's the right beam if you block it. Oh yeah, that's real close, right? And so it's hard to tell that there's two there, which is good because we want them to sort of overlap each other, right? But if I block that reflected beam, you see it kind of flashing there. And so very small tweaks can be done using that mirror. There's a XY alignment on the back of it, right? Which is what I was using. But I've also found that if I just move this lens, this L2 lens, if I just wiggle it around on its stand, I can fine tune it to be
Right here.
Yeah, right here. Yeah. So what's important is as the optics go down, or excuse me, as the beam goes down through the optics, those convex lenses, they cause it to sort of the beam to sort of go up and down. It's not perfectly flat, right? I mean, that would be ideal, but we could be here for hours. So the beam goes down, hits the rotating mirror, goes down to the fixed mirror, comes back, and it lands right where it was. So in theory, that beam is traveling back through here and then up through the microscope housing, right? Okay, so I've got this little camera here, should be working, I think. And so if I take the eyepiece out, so this housing has the ability to remove the eyepiece like this, right? If I take the eyepiece out, and let me see if I can move my, actually I'm going to put this on there first.
So our exclusive PASCO screen there.
Yeah. And so let me adjust the exposure so we can see it.
So it is just tissue paper.
Yeah, so what I've got there is just a piece of tissue paper. Right? And so like what I did was I took 2-ply toilet paper and I peeled it, and one of those plies is perfect for this, right? But you can see there's a bright spot right in the middle, right? And so that bright spot is that beam coming back, and that's what we want. In fact, what we want to do is try to get that bright spot right in the center of this opening here, right? And so,
pretty close.
Yeah, it's pretty close. So, but I'll just adjust the beam splitter just a tiny bit, and adjust the micrometer just a tiny bit, and so that should be good. And so what we can do is we can put this eyepiece back in there, and now I'm going to put the polarizers on there, because if we looked in there right now, that full laser beam would, well, it's not full, but the bright laser beam would go.
It's not a good idea.
It's not a good idea.
It's not
Yeah.
that bad.
And
the
so
magnification of that eyepiece
is 9. I think it's 9. Is it 90?
That's what I remember.
Yeah, 90, right? And so let me change my webcam to be a little bit brighter. There we go.
So
And
this
so-
webcam part is optional, right? But
Yeah.
I think it'd be a good thing to add to
Oh, yeah.
your lab setup.
Yeah, so I mean, students in the classroom, when they do this, they're looking down the eyepiece with their eye,
Yeah.
right? So I'm up in the front of the class and I want to sort of demonstrate this. This is the perfect way to do it. The one thing that I want to do is make sure the reticle, so there's a cross pattern in the reticle in that eyepiece. I want to make sure that one of those lines is aligned with the bench here. So I'm just going to peek in there and just turn it just a little bit. And so let me see if I can slide that back on there so we can see it. Oh, thought about it. But now you can see some of the follies associated with,
I can see that.
yeah, using, oh, of course I had to touch it. One more. There we go. So, let me just focus a little bit. There we go.
And you get some interference fringes and things
Yeah.
from some of the internal reflections and
Yeah, and we've got those polarizers on there, so the beam is really, it's dim compared to what it would look like normally. In fact, there's some background light that we can't see because the polarizer's knocking it out. But that's the bright spot that we're looking for, right? That's the bright spot that came back through. And you can focus that bright spot, right? So if you adjust the position of this mirror, right, it changes how that beam gets
Slightly.
collimated. Yeah, just
mean
slight
that
tweaks.
lens?
What did I say?
mirror.
I meant the lens, yeah. So that if you adjust that lens, and also, well, here, let me show you what it sort of looks like when the mirror is rotating. So we know the alignment's good. We're ready to start our experiment. I'm going to start this mirror rotating, and then I'm going to cover it up. Well, I'll leave it open. It's okay. It might be noisy, but so we'll start it, and you can't see it anymore. That's because you got the polarizers there. If you just pop those polarizers off of there. Yep. Yeah, and so now you can see there's the spot, right?
It shifted.
Yeah, it's moved a little bit, and it should have moved a little bit, right? Because that mirror is rotating now, right? And so there's a couple of things in this image that I want to point out here. Let me shrink that so we can see it better. First is that background red, right? So we've got lots of reflections off of surfaces happening, and so we get this sort of exposure behind that bright spot. And then there's that bright line on the left there. And so that bright line is from the beam, the point at which this mirror is rotating, where the beam comes straight down and then goes straight back through the optics before it makes its way to the mirror down there. And so it's sweeping across the optics before it goes down to the mirror.
So you couldn't see the spot if that was on the spot.
Exactly. And so we can move the spot around by making small tweaks to our optics here. If we just twist the lens a little bit, it moves everything around, changes the focus. Right?
So if you line it up too well, you have a problem, is what you're saying.
Yeah, that's right. If it's perfect, you might have to redo it. So, but this is exactly what we're looking for. And what students are going to do is they're going to align that bright spot right in the center of that reticle, so right where it crosses. I mean, they don't have to. Basically, this spot is going to traverse up and down in the screen here.
Yeah.
And so we need to measure the distance that it traverses, right? And so we do that by measuring the initial position and the final position on that micrometer when it was rotating clockwise versus rotating counterclockwise. And so I'll make some tweak. Oh, and you know that's the right spot. It should go away if you block the beam in between the two mirrors. So if you go right here, see how it disappears? Yeah. But that bright line doesn't disappear. That's how you know you got the right spot. And also, in part of our setup, when we had the tissue over there, to make sure that's the right spot, you want to do that same practice, and then you'll see it sort of flicker. That means you're doing good, you're ready to go. So I'm just going to adjust the micrometer and the beam splitter. The beam splitter is a little harder to adjust, but I'm going to try to get it right near the center of that reticle, basically. And so now we're ready to sort of make our first measurement, right? And so on this motor controller, there are two buttons. One of them starts it, stops it, and makes it go max revolution. And then one of them changes the direction from clockwise to counterclockwise. And so the first measurement we're going to make is when this thing is rotating clockwise at full speed.
15.
Yep. And so here
You wait until the very end for that, because that's what can overheat the motor.
Yeah. And so I'll put that housing on just to keep it a little quieter, because it's going to get loud. And so I'll hold this button down, and then it starts to speed up, and you see the spot move. So as the mirror starts rotating faster, the position of that spot changes, right? Because when that beam returns, light goes off of the rotating mirror down to the fixed, and by the time it comes back, that mirror has turned just ever so slightly. And so we adjust the micrometer to put it back in the center, right? And then we record that value, and it looks like it's about 12.69. So about 12.69. So if I go in here and I say 12.69, I've got the value already in there, right? Now we'll hit the direction button. You see the spot moving? So the rotating mirror is slowing down, and then it stops temporarily and it'll disappear. And now it starts spinning the opposite direction, counterclockwise.
The band disappeared too.
That's right, and the band disappeared. And now, once this thing gets up to 1500 revolutions per second, we're going to track that reticle back to the beam position, that spot position. And so we'll just adjust this to put it back up there, just like that. And this is our second measurement. So we'll read the micrometer, and it's 13.33. That's
by
millimeters.
reversing it, it's kind of like getting double the speed out of it.
Right.
So it's like you just had one direction at 3,000.
Yeah. And so I'm going to hit stop because we're done. We're done making measurements. And you'll see the beam sort of disappear, right? And then it should, boom, go away because we're no longer aligned with that mirror. And you'll see here, I punched in my values, right? So my micrometer values, it's in millimeters, right? So one was 12.69 millimeters, right? And the other one was 13.33 millimeters,
yeah.
Right? And so this equation that's in this file has A coefficient value, or constant value, D constant value, and a B constant value, right? And those correspond to physical distances between the optics.
Focal lengths and focal length minus the distance.
Yes, exactly. So it's the distance between those two mirrors,
Yeah.
minus the focal length of that one. Yep. And so I pre-measured all those, right? And
And the
punched it in.
manual explains that really well, so students
Oh, yeah.
can definitely understand what they're doing.
And the math, the physics isn't terribly complicated, right? Because like I said, it's really a mechanical system. And so the algebra can be extensive and the geometry can be complex, right? But once they've sort of laid it all out there and the manual does this for you, you know, students can derive this relationship all on their own if they wanted to. And so I used this equation here, right, which is in the manual, and then I pre-measured the A, B, and D values, punched them into my calculator here, and then I just punched in the 2 micrometer measurements I made, and I'm
That's pretty good.
My
yeah.
experimental value is 3.015 times 10 to the 8 meters per second.
Better than Foucault.
Yeah, so it's an amazing apparatus for accurately measuring the speed of light, and it requires some setup and some alignment that can be needs to be fine tuned. But once it's set up, we could run this experiment again. If I turn it back on, right there's the spot. It comes back and we're ready to go again.
So you know why Foucault developed this system? What was he trying to do? Was it just measure the speed of light?
Well, what do you mean?
Well, he had an ulterior motive. This is the mid 1800s, and there were a lot of experiments showing light was a wave, but people still, Newton was still held in very high regard. He is today, but his theory of light said light was a particle.
Oh,
right?
the corpuscle,
and
right?
to explain refraction for particles, they'd have to speed up going through glass or water.
That's right.
And waves would have to slow down. So he wanted to show the speed of light was slower in water.
That's right.
So if you were to have part of the laser path go through water, you could show that. So he wasn't really interested in the value so much, but that it was slower.
Yeah.
And he was the first to show that, and it was a pretty big deal.
Yeah, and there was a succession of sort of ideas and experiments to measure the speed of light.
Yeah.
And this was the culmination that proved to be extremely accurate.
And then earlier this morning we did Photoelectric Effect,
That's
which
right.
shifted things back to
Wait, it can
particle.
be a wave. It can be
Although
a particle.
I was reading, apparently photoelectric effect can be explained just by quantizing the energy levels in the metal.
Oh.
And you can use classical field theory, but at the time they were using it as evidence for photons.
So that is this system. Does anybody have any? Were there any questions?
No questions, JJ.
No questions. Well, thank you very much, everybody, for joining us for the speed of light.
What's next?
Yeah, we have some more great stuff to talk about. We're going to talk about microwave optics, and then we're going to talk about diffraction in just a minute. So,
Stay tuned.
Stay tuned.
welcome back, guys. Thank you for joining us today. JJ and I are, again, I'm Waqas Saeed.
JJ Plank.
And we're going to be looking at microwave optics. Now, this equipment looks pretty cool. And, you know, the sound of microwave optics, I mean, when I heard microwave first, I think of, you know, a thing in my kitchen, he reheats my food. This does not reheat my food, but it is a good demo to show how waves work. And you can think of microwave optics as a blown up version of light optics. We're looking at everything at like a much bigger scale. For example, I'm going to jump into it real quick. Like for a diffraction slit for light, we're doing another demo and we were looking at 600 slits per millimeter. Whereas like for diffraction for this, we're looking at these two slits and they're like, you know, 5-6 centimeters apart.
Yeah,
So,
it takes optics wavelengths of light that were, you know, really small, and now it's much bigger. In fact, it's the size of a microwave, right? So the wavelength is about 3 centimeters, 2 point something centimeters.
Right. And this particular, so we have two pieces. These are our key pieces here. This is our transmitter and a receiver. So the transmitter is what's creating the wave. The receiver is what's picking it up. Transmitter transmits, the wave is about 10.5 gigahertz. And it's only about 15 milliwatts, so it's not a strong wave, but you know it's there. And then everything we're doing, we're setting transmitter receiver. It's somewhere between, you know, like up to about 1 meter apart. So, you know, they're not too far apart, but it's strong enough to pick up the signals at about 1 meter.
Yeah, and the transmitter and receiver, they're not overly complicated. It just uses diodes, right? So one uses a gun diode, the other uses a Schottky diode, and creates microwaves linearly polarized, right, in the direction that the diode is physically oriented in, right? And then it's receiving them using a diode, again, linearly polarized in the direction that the diode is physically in. So we're creating them here, we're receiving them here, and the polarization plane that they lie in sits in the same plane that the diode itself sits in.
And what's very important is that in order to get the correct reading, or at least the strength of the wave, like the full strength of the wave, these need to be oriented at the same angle. And it's a little bit hard to turn right now, but you'll see one is a little, you know, one orientation that sits a little bit wider, one it sits a little bit taller, and I can easily rotate these. We have a degree indicator on the back, so I know what angle I've turned this. We're going to start off with both of these at 0 degrees. Then at 0 degrees, like my unit here has an LED at the top. That's where it's oriented correctly. And on the receiver, we have the meter oriented on the side. So it's very convenient for you guys to see. For us, we'll have to peek our heads over and take a look at what the reading is. And what's important is, so the wave, there's a slit in here that's like, the slit is like this, but the wave is actually traveling up and down like this.
Right. Yeah, and there's inside each of these is a resonator, so there's a resonant cavity in there that diode sits in, and these horns are just waveguides for those microwaves. And so we point them at each other, and one sends the wave, one receives it, and although the diode is sitting about back in here, and then the same thing with this one, the effective point at which it's being received, because of the geometry and the waveguide and the resonator, the resonant cavity in there, it's about 5 centimeters from the front of the horn here. Right?
From the front of the horn.
Yeah, and so when we make measurements, we can say, hey, this wave is being generated here, and it's being received here, right?
So, a really quick setup, like, so the first, so the manual that comes with the experiment, it has, I believe, 12 experiments that are included with this. So this can do a lot for just ordering one equipment set. The basic system comes with what you see here, you know, the receiver, the transmitter, some, like a reflecting lens, polarizers. It comes with a few of these things. If you buy the advanced kit, you'll get this unit for Bragg diffraction.
Yeah, we've got, I mean, it's basically an optics system. So if you had like an optics bench that had things like mirrors and, you know, diffraction slits and stuff like that, prisms, this has that, but it's just feels and looks a little different because it's on such a different scale.
Yeah, like the prism for this is actually this styrofoam, prism-shaped object here, which we filled with pellets of polystyrene.
Yep, styrene pellets.
Yeah.
Yep.
So this is a lot bigger than your prism for optics, but the experiment is very, very similar.
I mean, we've got this is masonite, right, with a melamine cap on it, and it's a partial reflector, right? So when we put this here, some of the microwaves are reflected and some of them are transmitted, right? So we can do experiments that has to do with refraction, right? Or we can do things like Brewster's angle if we want to figure out what.
Or the Michaelson Interferometer.
Yep, or we can use the Michelson Interferometer. We can configure this to be an interferometer, right? Just like we saw in yesterday's demonstration, except instead of laser light, we're using microwaves.
Yeah, awesome. So let's jump into the first experiment just to show you like a really quick example or demo of how this works. So what we're going to do is we're going to set these two about 40 centimeters apart from at these points.
At the diodes, yeah.
So it doesn't have to be exactly 40, but
And so in the manual, in all of the experiments, it recommends sort of a calibration procedure. It's not technically a calibration, but you set them to 40 centimeters, and then you adjust the settings here. So there's a gain setting on the front of this receiver here, and it's got a 1x, 3x, 10x, and 30x setting, as well as an adjustable gain here. And so you move them apart 40 centimeters, you adjust this gain setting, and then you adjust this line to set it to 1 milliamp on the scale here. And so there's an analog meter, ammeter here. You set it to 1, and then you start your experiments. So you've basically calibrated the system to be, to give you measurements that are readable.
So for the first experiment, it outlines, as JJ mentioned, we're going to set it to about 40 centimeters, and we're going to just take measurements at every 10 centimeters. We're going to take a measurement of the meter reading and the distance. Now, what's important is there's really 3 readings that we're going to be doing consistently on these. It's going to be, well, 3, 4. It's number 1 is the angle, so the angle at which these two are to each other. The second one is the distance, how far apart they are. Third one's going to be the angle of the transmitter, and then the angle of the receiver.
Right.
Did I miss any?
No, so they're polarized, right? So the microwaves that are coming out of the transmitter are linearly polarized, right? And so if the receiver is at an angle, tilted at an angle that's not along that polarization axis, then your measurements are going to go down. And so if it's set to 1 here, if you just twist that one, you'll see that the reading goes down. And when they're at 90 degrees to each other, it's 0, right? And so when we talk about that angle in between them, right, there is a graduated angle scale on the back of each of them that we can use to measure the difference between those transmission axes.
Yeah, so the first experiment just gives you an introduction to how the system works. The second one is actually where we're doing something a little bit more creative, which is reflection. So we're looking at how waves reflect. So we're going to have a difference of angle about 45 degrees. Going to...
And you'll notice if you can see that the measurement on the analog ammeter here has gone to 0, right? Because the microwaves are going off in this direction. It's just like if you had a flashlight or a laser, right? The laser beam goes over there, we're not seeing it anymore.
So a lot of our pieces here, they're modular. We can arrange them in many different orientations. This base has a little hole in the middle, and that's to put it right dead center of our goniometer here. And it's magnetic, so if I attach a reflector on here, it's magnetically on there. So I can go ahead and put this on here. So it says we're going to adjust these to be about 45. Actually,
yeah, we're going to adjust the angle, so keep that flat like that, right? And then we're going to measure. So if this is at 0, right, 180 degrees. Whoops, that's 160, right? Right, you can move these and then adjust this mirror until its maximum, mirror, I call it a mirror, right? And now we can measure the incident and the reflected angles here, right? And we can demonstrate or prove the law of reflection, right? Even though we're using microwaves instead of like a laser beam, right?
Yeah, so we're, what we can do, like, let's go ahead and do the first one. Let's set this at 20-degree angle of incidence, which is 20-degree difference in angle of where the beam is coming and the reflector here. And then we can slowly rotate this and figure out where we can get the maximum reading on our
so that
receiver.
Right. So yeah, it would be 90 minus 20 is what you got right now. Right. Yeah. And so we just swing this around. You see it was maximum right about there.
Okay. And then we just go through, you know, turn this at 20 degrees offset, 30, 40, 50, 60, and so on.
Yeah. And so for real shallow angles, right, you can have this goniometer collapse like this, and so this looks like it's about 25 or 30 degrees in terms of angle of incidence versus angle of reflection. And so we can adjust this to be maximum and then measure those angles, record them, law of reflection.
Experiment 3 in the manual is standing waves. Now, standing waves are important because you don't really think about it when you think about a wave going out, but what really happens is, you know, when a wave leaves, it can obviously bounce off the surface and come back. So standing wave is at that point where the wave that's coming back has this, or it's changed by about half a wavelength. So the wave coming back actually interferes with the wave that's being transmitted, and at that point we call it a standing wave. So the way we can measure a standing wave is as we slide this, we'll see that the reading on the intensity, it's going to go, you know, it's going to go up and then back down, then up and down at different points across the meter. Yeah. And that minimum is, that's the point where we're at a standing wave.
Yeah. So these resonators and waveguides actually act like a reflector to some degree. So the microwave is emitted, comes down, it's received here, but some of it gets reflected back, right? And so we get this bouncing back and forth between these waveguides of those microwaves. And the wavelength is fixed, right? And so if we can get the distance between them just right, we can set up, you know, standing waves in between these two waveguides. And that's basically what you do. And as you adjust.
So yeah, if you take a look at the screen here, we'll go ahead and just slide one over, and you'll see.
Yeah, and so it's going up, down, up, down, up, down, and you'll see that every time it goes up and down, you're cycling in and out of that standing wave relationship, right? And so you'll see that about every half of a wavelength. So every time you move this thing, and remember it's going down and reflecting back, so every half wavelength you're cycling through. So every time you see maximum amperage to maximum amperage, the distance that you've moved is half of a wavelength, right? And we know the wavelength. And so we can demonstrate standing waves.
The next thing is refraction.
I'm sorry. No. And you can also do it with a reflector too, right? So these act like a partial reflector. It works, but you can use a mirror, right? Just like if we had a rope tied to a wall, except there might be a phase shift difference.
Next thing, let's look at our prism example that we talked about. In order to use that, we're going to have our, this is called a rotating table. This comes with the basic kit. It has a little notch on the bottom here, and that's so we can keep track of the angle on the goniometer. So let's go ahead and set that down. That was 0 degrees. And now for this, the angle doesn't matter, but the angle for this is really what we're looking at. And we are going to set our prism here. So the transmitter is going to send the wave to the prism. We're going to have an incident wave, which is the angle.
Yeah, so the microwaves come straight in here, right? And the medium where they're going to experience a different index of refraction is it within these pellets here, right? Oops, one just fell out. And so the microwaves come through this surface perpendicular, so it doesn't experience, right, a change in direction. but then it hits this surface between the polystyrene and air effectively, right? And so it's going to experience a change in direction, right? And so the normal line is in this direction. We've got some incident angle, right? And so we can adjust this, right, the angle of this receiver to a position where it's maximum, so right there. And so you can see that there is a little bit of a change in angle there, right? And
so we have our angle of incidence and our angle of
refraction.
Refraction.
Yes.
Yeah.
Yep. And then we can, you know, we can demonstrate Snell's law using microwaves.
Perfect. And then the next thing we can do is polarization. Now we talked about polarization at the beginning. So the simplest way to show polarization is what JJ mentioned, is, you know, by turning one in, by turning one of these. So actually, I'll turn the transmitter so you can still see the meter here. So as you'll see it, we're at, you know, pretty high value. As soon as I turn this, I'm gonna go to 0. Now this is where the polarizer comes into play. Let's go ahead and put this here.
Yeah, and so you can, just by turning the horns or turning the transmitter or the receiver, you can measure the angle there. You could do a Malice's law experiment, right? Where you can show that the strength of the intensity squared times the cosine of that angle in between them, right?
Yeah, we can actually, we can turn this,
intensity.
you know, 10 degrees at a time and just get the reading of our intensity. And yeah, as JJ mentioned, use Malice's law and go about it that way. Now the other quick way to show polarization is to use the polarizer here. So we can see, so we should be getting...
yeah, so they're 90 degrees to each other, right?
Yeah.
So
they're 90 degrees, so we have no signal
Yes.
that's being picked up.
That's right.
I'll put this right here with the slits this way. What's our reading?
It doesn't change, right?
Nope. So let's change it horizontal.
Yep. Still no change,
So
right?
no change. Now here's the trick. Let's put it at 45 degrees.
Yes, and now you can see that the ammeter has jumped up some, right? And so what we've got here is the microwaves come out polarized in this plane, right? And they need to be received in this plane, right? But that 90 degrees means we're not going to see any microwaves with this receiver. But as it travels through this polarizer, right, there is a component in the direction of the polarization angle of this. And so that tiny little component does get transmitted, but it's sort of projected onto that polarization, a different polarization plane, right? And then that component will be seen. There is a component of that will be seen by this. And so you can see that by adding that polarizing filter in between at some intermediate angle, that all of a sudden you're seeing light, or you're seeing the microwaves. And the same thing would happen with, you know, light optics.
And we can also do this with, the experiment comes with 2 polarizers, so we can actually have one at, let's say, like 22.5 degrees, and the other one at around, what, 66
Sure.
degrees, and show the same thing that way. The second one is staying in there.
Yeah, and also you can demonstrate how, you know, Polaroids or polarizing filters work, right? So you've got this. So the waves are polarized. They make it through this because that axis, that polarization axis, is the same as the transmission axis for this polarizing filter. But as soon as you put one in there that's perpendicular to it, now it doesn't make it through, right? So you can demonstrate how polarizers work.
We can also do interference with this. So double slit interference. As we showed at the beginning, this is our double slit apparatus here that we created. The experiment will tell you to try to set these about 1.5 centimeters apart. So you want to try to be as exact as we can. Let me go ahead and.
Yeah, because when the slit width is on the order of the wavelength, you know, things start happening.
Physics happen.
Yeah.
So,
Let's scoot it over just a little bit.
so as we learned in the polarization experiment, the waves are actually traveling this way. So we need to rotate these 90 degrees so that they'll actually make it through our double slit slits that we created.
Yeah, and so you can then, I'm going to move some of this stuff out of the way.
So this part will be hard. You'll kind of have to take our word for it just because of the camera angle.
Yeah, so then I can move this, I can swing this receiver around, and the amperage, the ammeter that's being read here, goes up right here where a 0th order maxima would be.
And when he says it goes up, I mean, we're talking like 0.4
Yeah, it's small.
milliamps. Like it's a small change.
But then if I keep swinging it, I'll find another area right here where that reading on the scale here goes up again, right?
And
so,
again, we notate that same angle and
yeah,
do it the third time.
so we could have a 1st order maxima, and then we keep going way out here, and there's actually a 2nd order maxima out here, and then we can use that relationship, right? That right.
Yeah, we can record the intensity, record the angles as we sweep across this point.
Yeah, the
make
spacing.
a nice graph, and we have our diffraction pattern.
Lambda equals a sine theta.
Lloyd's mirror. This one's kind of cool. So what this one is we're going to set the receiver and transmitter pretty far apart. It's saying at least about 1 meter apart, and normally we would use our extra track right here. Let me see if I can actually set this up. But essentially what we're doing is so we know that when the wave leaves our transmitter, it's not just going straight to the receiver. There are waves that are being propagated outwards as well. So what Lloyd's mirror is we're actually taking a reflector and we're going to be moving it towards the wave here. And actually what we'll see that the intensity will increase. It'll fluctuate a little bit, but it will change based off of the position of the mirror.
Yeah, because when that distance is just right, you get reflection back, away from the transmitter, back towards the receiver, so you get this sort of constructive interference right here.
So that's another, so we can, as we change this distance, we can, notate what the intensity is and get a nice graph that way. Next.
We have a question, guys.
Yep.
Yeah.
What would happen if you placed the 3rd polarizer between the 2 cross ones at a 45 degree angle?
So the idea is that you would see the same thing that we saw earlier when we put the 2 horns at 90 degrees and put one in at 45. Right, that same thing would happen. The problem is you lose a lot of intensity by doing that, so it would be difficult to detect it. But yes, that you should be able to see the same phenomenon. But we tried that earlier, and it was difficult to see it. It was much more dramatic when we just used the horns and a single filter at 45 degrees.
And the more plates we add in between, the more of the signal we're losing.
Yeah.
So the next step, Fabry Pro Interferometer. So with that, we can use the 2 the partial reflectors, and place them here. We can adjust the distance in between, and just to figure out where we're getting the maximum intensity. As well as after that, we're looking at the Michaelson Interferometer. That one, it does take a little bit of time to set up, so we're gonna skip over that part today. But it's a similar thing to the laser interferometer or Michelson interferometer that you saw, where we're using the partial reflector in the middle. It's putting some waves in this direction, some waves in this direction, and the waves are bouncing back and forth. We're going to be picking up the intensity on one side of it and reflecting on another. We're going to be adjusting that point.
Yeah, and as you adjust so you got microwaves. So this is the transmitter. The microwaves that come down, this will be at 90 degrees, right? So over here, you've got a mirror. So one of these silver pieces over here, and then a partial reflector in between. This acts like a beam splitter, right? We send some down this path, right? We send some down this path, and as they collect, they meet down here by the receiver. Depending on the position or the path length difference, you'll get constructive or destructive interference at the receiver. So as you adjust it, you'll see that the meter sort of fluctuate, just as you would with our regular interferometer.
So JJ, what's this cool thing over here? This bag
Oh,
full
yeah,
of
right.
plastic pellets.
So the Prism was filled with those styrene pellets, right? And so one other activity that you can do is the system comes with these bags, these long bags here. You can fill them with the pellets and create a fiber optic cable, basically. And so now we can take this and, you know, bend it to some angle, like that, let's say. And so if you here, slide this one back just a little bit. There, that's perfect. Yeah. Too much. So if you hold this end of the cable, go ahead.
Yeah.
Hold it into the light, the beam of light. You can guide it back over here. You can see as I move the fiber optic cable into the receiver, you get a reading. If I take it out, it goes to 0. And so you can demonstrate fiber optics with this using these styrene pellets in this bag. It's pretty awesome.
And even when they're facing each other, we can put our fiber optic cable in between to see how it will actually help the wave. Like if I don't have, let's change our scale. I'll actually take that back. Maybe it didn't help the wave.
Well,
They've gotten that far wrong.
So fiber optics, right? You can talk about total internal reflection, right? Those microwaves go into the cable, this cable, and they stay in the cable as long as you don't bend it too much, right? So you can demonstrate. This bag's a little too full, right? If I bent it even more, I think it would probably rip. But you can demonstrate, you know, these microwaves can make it around corners by using a fiber optic cable just like this. So without the cable there, you get nothing. With the cable there, you get a reading.
So all of these can be done with the basic system as it comes with. We do have a few optional accessories that you can buy. The first is this microwave probe. What this allows, you can actually connect this to the receiver and put it in place of the receiver as like an antenna for receiving signals.
Yeah, this microwave probe connects to the receiver here, straight into the bottom, right? And so you can use this thing to probe different areas to measure the strength of those waves or the intensity of those waves. And then the same analog meter will measure those for you. So we're railed here. Turn that down just a little bit. And so if you want to explore nodes and antinodes in a standing wave, right, you can take that standing wave experiment, set it up so you've got standing waves, and then you can slide the probe through here, right? And so some of the waves are being measured, right? The strength of those waves is being measured with this diode, and some of them are making it through and still reflecting. And so you can find the areas where you've got maximum amplitude versus zero amplitude, right? Nodes and antinodes.
Now with another accessory kit that we have is it comes with this polyethylene panel here, as well as the Bragg diffraction unit here.
For crystallography.
Right. So this is similar to like what our Prism was made out of. You know, it's made out of plastic that's adjusting what happens with the wave. It doesn't completely block it, but it does allow some of the wave to go through. We can actually put this on our bench here, and this is where we need that meter on there, because what we're going to do is we're going to adjust the angle between angle of incidence and angle of refraction between our panel here and the receiver, and you know, doing the same thing. We're sweeping across and looking for minimums and maximum across as we adjust the angle. But what's important here is that we need to adjust, for this experiment, we actually need to adjust the angle of both of these. So for every 1 degree I adjust this, I need to adjust this 2 degrees, because we want that angle to be similar. We want the change in angle to be similar relative to both. And then the last experiment is Bragg diffraction. Is where we're using actually this unit here. What Bragg diffraction is you'll see these metal balls that are inside of this this unit here, and what this does is it changes where the wave is reflecting. So it's depending on the angle, the waves are going to hit each one of these at a different point, and it's going to change the amount of the wave that it allows to transmit through.
Yeah, you get, it's like a crystallography, sort of a crystal diffraction pattern, right? So we can use the transmitter and swing it around to different angles, and we can measure, right, what those, we can basically detect what that diffraction pattern looks like.
So I mean, you get the basic pattern here. I mean, this thing is pretty all-encompassing. There's a lot of experiments it can do. This isn't just for, you know, for one day of physics. I mean, this is at least like a few days in the lab, especially when, you know, students are recording data, they're analyzing the data, they have to make the charts. I mean, there's a lot of homework to be done here, and it's cool. I mean, you can decide what you want to do with the optics. You can design the kit to however you want to use it in your classroom, and it's a much sometimes it's a much easier way for students to grasp the idea in their mind of like a wavelength, because by adjusting this, you know, 2 or 3 centimeters, we can see the wave change versus like adjusting a micrometer on a little handle and trying to figure that out with light. But we actually will be doing something like that next, but you know, jump into that. But yeah, are there any questions from the audience on any of our on what we've shown you today?
We did get a comment if you could briefly show a standing wave.
Sure.
Can be measured using a reflector.
Sure, sure.
Put that in the center. Better?
Yeah, that's fine. Here, you be the probe man.
So just take a look at the intensity meter here as I go ahead and
Sorry,
I need to change.
hold it still.
I need to change the 38.
There. So go ahead and move closer. It goes. You can see.
So as I'm sliding this, you'll see the wave.
Go way up, way down, way up, way down, way up, way down, and you'll see the difference between one high amplitude spot and another one is half of a wavelength.
And the proper way to do this actually is 2 of these. There you go. So yeah, we can just slide this back and forth, and then yeah, we'll see the intensity change on there.
Okay. Yeah.
Move this back a little bit.
Yeah.
There we go.
Now move that.
There we go. There's a maxima. Right there. There's a minima right there. So that's the point where we have a standing wave. And as I sweep across, go another about 1.75 centimeters at another maxima, and as I go again, there we go.
Yeah.
Another standing wave. Any other question?
They're asking if the sensor is included in the standard kit.
This one is not. This is an optional accessory.
And that the diode that's used in this probe, it's highly sensitive to electrostatics. So if you do get it, be very careful. You know, have students mind what they're touching. The sensitive area is that diode right in the center of it there. Otherwise, you know, handling it out here in the semiconductor is not a big deal.
All right. Well, if that's it, then thank you again for joining us. We have one more experiment that's going to happen after this. We're looking at the wireless diffraction scanner. So we'll be back shortly to show you that. Thanks.
All right, here we go. We're going to do interference and diffraction. My name is Brett Sackett with PASCO, and my partner in physics is
Ann Hanks.
All right, so let's talk about the interference and diffraction setup. This has our newer wireless diffraction scanner, and so it is compatible with our optics bench. This is the same optics bench that we use for basic optics with lenses, and there's lots of different attachments you can get for it to do things like black body or atomic spectra. This attachment is for interference and diffraction. And so, Ann, do you want to talk about the device down there?
Well, it's the nice thing about it is it's so easy to set up. Even a baby could do it.
It is easy.
Because you just slide it on, it's all ready to go. It's got a translator here where we keep track of position, and inside here is a light sensor, and then there's an adjustable slit width on the back. Nice thing about it being wireless is you don't have to worry about, Brett's been carrying this around all week. Anyway, there's a knob on the back here so you can select what mask slit is in front of the light sensor. And then you're going to tell them about the new set of slits?
So it's an all-in-one device that includes the light sensor, includes the position sensor. The position sensor can resolve 0.01 millimeters of translation as you scan across your diffraction pattern. And then we have a number of slit accessories with these rotary dials that allow you to select different types of diffraction slits. And this one here is a combination of single slit, double slit, and there's some other interference patterns on here as well. I don't know if the camera can pick that up, but this dial here, you just rotate and select which pattern you want to go for. So this attaches right here. I'm going to flip that around.
Yeah, that's where I use it.
Yeah, so and I just flipped that around because we have some indicators on here which you're going to use to measure the distance from the slits to the aperture bracket down there. And so I'll move this around because what I want to do is I want to measure from where the laser is going to pass through the slit pattern itself. So and you can just position that. When you do the geometry of this, you're going to have the students measure the distance from the slits to the aperture, and that'll be part of their calculation. So then on this side is where we put our laser. Now we've got a couple different wavelengths here. I have a red and a green, and so we'll start with the red laser. We just position this, and if I fire that on, you see that the way these are set up is they're already aligned. Now this laser does have XY adjustable positioning, and so you can do that to aim where it is. But the first thing we want to do is we want to we want to align it with the aperture bracket there. And so typically what I'll do is I'll remove the slits, and you can see how it's aligned. Right now the laser's coming in a little low, and so I'll use the Y, that's not the Y, that's the X. I'll use the Y adjustment to raise it up a bit. So you want to aim it right at the center of the aperture, and then when you put your slits back in, you see we have a real nice diffraction pattern. And let me do this. You want to translate it over a bit, and I'll just go through some different patterns so we can see what the different patterns are. So if you can focus on the diffraction patterns, I'll just kind of rotate through a couple different ones, and you can see with the we've got some single slit, we've got some double slits. There's a nice wide double slit there.
I think that's multiple slits. That's why.
Oh, okay.
Yeah.
And then you'll see we've got some other diffraction patterns that are two-dimensional diffraction patterns. There. Okay. So now, is that on?
Yes.
Okay. Now the wireless diffraction scanner is, you can use it connected via Bluetooth or USB. There's a USB port on the side that you can connect it directly to your computer. Right now we're going to use it wirelessly, and it's rechargeable, so you use the USB connector to recharge it. Okay, so so what I'll do here is I'm going to set up Capstone. So it's so in Capstone I can see it's an available wireless device. I'm going to select that. And so now I can see here's my diffraction scanner. It's fully charged, which is nice. And then I've got my diffraction position sensor and the diffraction light sensor. In the graph here, I'm plotting light intensity on the y-axis and position on the x-axis. And so here we go. So I think we're about ready there. So what I'm going to do is, now we're doing, this is a single slit,
Okay.
which is, it's pretty broad. In terms of the definition of the interference pattern that you're measuring, it's pretty broad, so you don't need a super narrow aperture. So on the aperture there, in this case, you might open it up a little bit.
Is it at 0.3?
It's on 0.3, so we're going to go with 0.3. So I'm going to hit record here in Capstone. And then, Ann, if you want to scan across. And what we've done is we've turned off this bank of lights that were right on top of us. And so there still is some ambient light in the room. And when you're using that dial to scan across the diffraction pattern, you can grab the handle and kind of move it very finely, and you'll find that when you get to some of the peaks, you may want to slow it down a bit so you make sure you're capturing. And we definitely maxed it out.
Oh, too bright?
Yeah, so that might have been too bright for that pattern.
Okay.
That's okay, because that's part of why we're doing this, because we wanted to show some of the tips and tricks of doing your scans. And so here you can see the light level down here is really low, so that's good. You can see our light floor is about here. Now if we were doing this in the lab, in the actual physics lab, we'd probably have it really dark to lower that light floor for everything. And so, and notice this is Ann zooming past, and you can see it tracks the entire pattern backwards. So that's really nice. And so we're gonna change the aperture, and so we're gonna, because we want to get that maximum peak there and see how that is. So let's go ahead and narrow that down.
Why don't you stop the recording?
There we go. All right, so we're going to do another scan. I'll hit record. And getting that peak is going to be very important, because when you look at the geometry of the interference pattern, the indices M1, M2, M3 are all measured from that 0th order maximum. And so we want to make sure we can find exactly where that peak is when we measure the data. So Ann's scanning across very patiently.
Yes.
Generating beautiful data. All right, here we go. It's going to zoom way up.
Did it max?
I think it maxed out again, but that's probably good enough to get a good idea of where the peak is. All right, so let's take a look at that data. We've got our 0th order maximum there, and then if I zoom in here, you can see I have a nice, beautiful scan there.
Ooh.
Look at that.
Yeah.
Love it. So what we're really interested here is the conditions for the minimum. And so I'm going to use my coordinates tool here, which I can use to gravitate towards that peak. I select this to turn on the delta tool, and I'm looking for minimums, and so I want to bring this down, and I'm gonna zoom in here a bit so I can see things a bit better. And you'll notice when I'm using this delta tool and I'm dragging this around, you see this arrow that's popping down, and it's looking at data, and what it's doing is it's attracted to the data, so you can just kind of zoom around and wait until that vector is at the point you want, and then release it. And now I can measure, this is my delta x to my m equals 1, right? So it would be m lambda d divided by y, and that measurement there is 3.97 millimeters. Because
So
we're doing single slit.
It measures default in millimeters then.
Yes, the default measurement's going to be in millimeters, so make sure when you're having students measure, they're doing their conversions properly. Let's try a couple different scans. That one was still peaked out a bit.
So
But that's part of doing these scans is adjusting that aperture there to get the. Let's do a. Another thing to keep in mind when you're setting this up, we are using quite a long distance between here and here, and that's to let that interference pattern spread out quite a bit. As you move this closer, the pattern is going to get closer together. It's going to be a little more difficult to resolve all the peaks.
and it also won't meet the requirement that this distance be
Yes.
much greater than the
Correct. And that allows for sine theta to be about the same as tangent theta, which makes the physics a lot easier. All right, let's try this scan.
What is this one?
I don't know, I'm just picking them. The dial tells you, what the slit width is.
Are you recording?
I am recording.
Okay.
Now you can also use your own laser and your own, if you have your own diffraction slits, you can use those. You'll have to, of course, do your own alignment there. Oh, look at that. Fantastic data. Look at that.
Is this another single slit?
Yes. So here again, we take that measurement, add a coordinates tool, bring it over to the peak, and do a delta down to, you might want m equals 1, maybe m equals 2, and make that measurement there. So then, let's try what if we change the wavelength. So I'll switch from the red laser, which I'll turn off, and now we'll use a green laser. And so if I pop that in and turn this on,
It's good.
yeah, so again, it's all aligned, so you don't have to fiddle with the alignment too much. Let's go ahead, I'm gonna hit record. Now if you started at the same point, you could have red versus green and see how they align. You just have to make sure that your starting position is going to be the same on the translator. Here it comes. We're starting to get little bumps.
What always amazes me is how, even though I can't see them here, it picks it up on the scan.
Yes. Yeah, and you can, you can adjust that aperture if you want to get more narrow and scan really slow, and you can get a lot of the really fine detail down in here.
Look at all the big peaks there are.
Yeah. So
off to the side, there's just lots and lots.
Yeah. So when you really zoom in, you can really see that interference pattern you know, your eye can only pick up so much. The light sensor can pick up a lot more, and that's one of the.
That's also one of the reasons that it's so good is because these are metal deposited slits.
Yes.
There's on
Good
glass.
slits, makes good patterns. But the, you know, one of the, I think one of the real teaching benefits of this is, you know, when I think back when I did interference and diffraction in school, and you took a laser through some slits, and you ended up with some dots on the wall that were projected, and you would measure, you know, from this peak to that peak, and that's really all you saw were these, you know, a number of different peaks that appeared on the wall. But what you're learning in the textbook is there's an electromagnetic spectrum. There's things in between those peaks. And that's what makes this really cool, is the light sensor is able to measure everything in between, so you can pick up all of the detail. Oh, I was still recording.
Oh, shit. Oh, great.
So let's find a double slit. Let's find a.
Can't you see what it is?
There we go. Right over here, right?
Yeah, that's a nice one. I'm going to put this on a finer.
Okay. So now we've gone to a green laser, right? So it's a higher frequency than the red. We're going to a double slit interference pattern. And so Anne's changed the aperture down because we're going to have a lot more detail in this scan. So we want to make sure that we're going to be able to pick up all that detail. So this especially, because there's so much fine detail we want to pick up, you do want to make sure you're scanning very slow so you pick up as much of the detail as you can.
This is really easy to turn, by the way.
Yes, it does feel nice. Now, some people have, when they see this kind of an apparatus, someone generally asks, oh, well, why don't you just put a motor on it, have it scan automatically? And yes, we could. That would make it a lot more expensive. We also want to make sure that students, you know, get that hands-on experience, and it's not just a black box spitting out beautiful curves. You know, we want the students to get their hands on the equipment as much as possible so they get that experience of doing the scan across. Oh, look at that. Man, that's some nice stuff there.
This is a particularly fine
Yeah.
pattern because it's green.
Yes.
The red would be spread out more.
Yeah. Yeah, with the green, it's a lot higher frequencies, and
So push stop on that one.
yeah, let's check this out.
Ooh.
So we'll just scooch this over. Look at that. And again, you can see a lot of the detail down in here. And probably for this, this would be another situation where having the room even darker would help quite a bit. Because we still have a light floor in here. Nice, that's a beautiful one. Let's see what else we got. How about that one? I do have in Capstone here. I do have
I want to see
another tab set up for the double
multiple
slit.
slits.
Sure, and you set it to whatever you want. Because that's what Anne does. She's the queen of physics, and she just does what she wants.
Okay, there's 5 slits.
Oh, there we go. So this is a 5-slit pattern.
Okay, you ready?
Are you? I'm ready. I'm always ready for good physics.
I can see the dots here.
Yeah, we're already picking them up.
Of course, with 5 slits, you're going to have n minus 2 minor maxima. So should be 3 minor maxima between these. Good enough?
Yeah, that's pretty good. So there's a 5-slit pattern.
Let's. So can you blow this up in here?
Yeah. So we'll expand this out. There we go.
Yeah, there should be 3 minor maxima, but we're not catching it because of the light.
Yeah.
Yeah. The one minor maxima is getting a little bit overshadowed by our extra lights here.
Yeah.
You turn the lights out though, you get beautiful, 3 minor maxima.
Beautiful diffraction patterns. All right. Okay. I think that's about it for interference and diffractions. Were there any questions? This one's pretty straightforward.
More questions.
Okay.
Questions get.
All right.
All right, thank you very much.
Hope you've enjoyed interference and diffraction with PASCO Scientific.